Hi everybody, I'm Greg Fishel and welcome to bonus weather video number 2 for this week. And as mentioned in the daily weather update, I'm going to go through a little bit of the detail that I went through yesterday in order to predict today's high of 103. I will admit to you that, when I looked around after I did all the recordings last night, it's like I saw forecast highs in the upper 90s, I saw forecast highs for 100, but nobody that I saw was going for the 103 that I went for, and I, started to ask myself, well, what am I missing, And I finally decided I wasn't missing anything, and I was going to go for it, and it hit 103 so far as we know at the airport. Sometimes it can sneak up another degree after the climate report comes out in the late afternoon, but it certainly was very, very close to that. So I want to take you through the process that I went through yesterday and let you know that there is science behind it. Okay, so something popped up there. It wasn't supposed to pop up, but luckily it went away. So we have talked about a lot in the last almost 2 years now about the concept of thickness, okay? And it basically says that if you have a surface of constant pressure, okay, where everywhere along that surface the pressure is the same. Think about this as a topography map, where let's say you want to plot a map of the surface that is 500 feet above the ground, okay? Well, obviously that surface is going to undulate, okay, because in the Rockies, 500 feet above the ground is going to be at a much different altitude than 500 feet above the ground at Riceville Beach, okay? So you have this undulating, wavy surface, but everywhere along that surface, whatever parameter you're looking at, is the same. So millibars is a metric unit of pressure, okay? So if you want to use inches of mercury, you can do that too. But in meteorology, we all use metric, and so 1,000 millibars when you're near sea level is generally near the ground. 850 millibars is about 5,000 feet up. And so the distance between those two surfaces of constant pressure is proportional to the temperature, average temperature of the layer between them. So the closer those surfaces are together, the colder it is, and the farther apart they are, the warmer it is, okay? So that's the basic idea between 1,850 millibar thickness or any thickness you want to look at. You can do 1,500, you can do 850, 700, whatever you want. In this case, 1,850, which is roughly the lowest mile of the atmosphere. Okay, so I'm not going to go through the whole derivation of the equation, but this is called the hypsometric equation. And it says that the natural log of pressure 1, one of those surfaces, to pressure 2, another one of those surfaces, times is equal to the gravitational constant, which is the rate at which objects accelerate as they move toward the Earth due to gravity. There's a gas constant, which has a value of about 287, and the temperature, the average temperature of that layer, times the thickness, okay? So in this case, P1 is going to be equal to 1,000 millibars. P2 is 850 millibars. The gravitational constant is 9.8 meters per second squared. Okay, it's an acceleration. The gas constant is 287. And we're going to say arbitrarily that the temperature is 273.15 Kelvin, which is the scientific unit that we use. And so when you plug all those numbers in, you get a thickness of 1,300.1. And I think I've mentioned this before, where 1,300 is used as a first guess or rough estimate as to where the boundary between solid and liquid precipitation will be. There can be some small variations up and down, but it is a very useful tool during the course of the winter to sort of give you a starting point as to where those boundaries may be. But that's another topic for another day. All right, so you plug all that in, you get 1,300.1. Now, let's increase the temperature 1 degree Kelvin. Everything else is the same. And Kelvin, the magnitude of a Kelvin degree is the same thing as a Celsius degree, okay? So let's increase it to 274.15. Now we get a thickness of 1,304.8, okay? So that means that 1 degree Celsius, averaged over that layer, is about 4.7 meters, okay? The thickness of it increases 4.7 meters, it warms up a degree Celsius. If it decreases 4.7 meters, it cools down 1 degree Celsius. But a Fahrenheit degree is only 5/9 as big as a Celsius degree, okay? So when you multiply 4.7 meters times 5/9, you get 2.6 meters, okay? So 2.6 meters of thickness is equivalent to about 1 degree Fahrenheit up or down, okay? So yesterday, these are the thickness values that we had yesterday at 8, 11, 2, and 5, and then those 4 averaged together. The forecast for today, using the American Ensemble mean, you can see those numbers there, 1419, 1425.7, and so forth. So the 24-hour change from yesterday to today was plus 18.1 at 8 o'clock, plus 17.5 at 11, plus 20.4 at 2, and plus 17.3 at 5. All of that averages out to plus 18.4. Okay, now that's meters, okay? So when you divide those numbers by 2.6, which we already discovered that 2.6 meters is equal to 1 degree Fahrenheit, you get a temperature increase of 7, 6.7, 7.8, 6.7, all that averages out to 7.1. So yesterday, as of the time of the taping, the high was 97. Eventually it got up to 98, but 97 was the number I had in my head, and so plus 7 would give you 104, and I backed it off 1 degree just because once you start forecasting temperatures that are near the all-time record high, you start to get a little bit nervous, okay? So I backed it off from 104 to 103. But that's the process that I went through, and this works really, really well in the summertime because usually the atmosphere is very well mixed over the lowest mile of the atmosphere in June, July, and August. Now in the wintertime, a lot of times the warming from the ground, in other words, the sun heats the ground heats the air above it, that warming influence only makes it up to maybe 900 millibars. So 1,850 is not a great tool because it's taking a look at part of the atmosphere that we're not concerned with. But in the summertime, when you usually are mixed over a much deeper layer, this works really, really well. So I couldn't, to be honest with you, understand why you wouldn't go for temperatures to get well above 100 with those kinds of thickness increases and associated temperature increases. So that was the process that I went through. Now, this only works when there's sunshine, okay? If there's going to be clouds and showers around, this all goes out the window and you have to account for that. But today, obviously, we didn't have any of that to worry about. And so again, it just made sense to me to up the temperature, 6 degrees over what it was yesterday, and it ended up working out quite well. So I just wanted to let you know what the process was that I go through, the science behind it, and we'll see, how things go from this point forward. But 1,850 millibar thickness was something I was introduced to by a gentleman named Elliot Abrams, who was once the senior vice president of AccuWeather, and I worked part-time up there when I was in college in the mid and late 70s. And he was the first one that told me about that, because prior to that, the thickness that we looked at was 1,000 to 500, which went all the way up to 18,000 feet. And it's always cold up there, okay? So if you use that for a rain-snow boundary, you're missing the boat. You want to take a look at the layer that's most important, that's going to make the difference between rain and snow and sleet and all that kind of stuff. So that was my first exposure to that, and that was what? 1975, so 85, 95, 05, 15, almost 50 years ago, okay? So time flies when you're getting old. All right. Okay, folks, that's it for now. That is bonus weather video number 2 for this week. Number 3 will be coming up on Friday. Daily weather update is already posted. Next one of those will be coming up tomorrow. Y'all take care, folks. We'll talk to you soon. See ya.